In either Tuesday or Thursday.
Thursday sounds good.
Thursday.
We have to worry about the test.
All right.
There's an exam on Thursday.
Yeah, there's an exam on Thursday. You know, we have exam 18 on Thursday. So this pH lab, you know, you just recorded some pHs, maybe did some calculations. When do you want to turn that in?
Which one is that?
That's the one that you use the pH meters, measure like 3 different solutions or something. And then you make the buffer, actually.
Is that the hydrolysis of the
Yeah, hydrolysis of salt.
I thought you said it was only observation.
Yeah.
Oh, really? All right, observations only. So this one, just leave in your notebook, right? And so this is not due.
And then we have the equilibrium.
Then, yeah, the equilibrium lab, that's right.
That's the one that you said it was.
That I said is due after spring break?
Yeah.
All right.
No, that's not titration.
It was the qualitative analysis.
Yeah.
That's what he said we do.
The one with the unknown?
Yeah, the one with the unknown is due this week, right?
Yeah.
Some people already turned it in, but if you haven't, what did I say, Thursday or Tuesday? Thursday, all right, we'll have it due Thursday.
And the equilibrium, you didn't say when it was due, but you said that you were not.
Equilibrium, you just wrote observations.
No, it's the one like
The color change?
the color change.
Yeah.
Color
Well, we have to
changes.
get it out at the
All right, this one you can leave in your notebook. I'll check that in your notebook. And so these two don't, unless you already filled in the form.
Yeah, I did this one.
Okay, then turn that in. All right, other questions? Any questions on chapter 18? Oh, Exams will be back, see, tomorrow or Wednesday. I haven't gotten all of them yet, so there's still one person who missed it, who had some kind of health problem. So I'll hand it back this week, okay? I can't post the key yet either. All right, well, if there are no questions, we're going to talk. If there are questions about chapter 18, we can answer those. All right, we're going to continue with kinetics. For kinetics, you know, we just measure the concentration of something versus time. And so if we're measuring the concentration of reaction with time, the reactant concentration is going to start off high, and then there are different ways that it can be composed. That is, it can be consumed. You know, it can be consumed in a linear manner like this. If it's linear, then it's easy to predict because we know what the rate is going to be at any point. You know, the slope here is equal to the negative rate. I should say the negative of the slope is equal to the rate. Rates are always positive, so that's why we have to change the sign here. And then we could fit this, you know, to an equation. In fact, the best definition for this is just this simple equation of a linear line, y equals mx plus b, where y is the concentration of A at time t, m is the slope. And the slope is, what is it, delta concentration over delta t plus b. And b is the intercept here. So that would be it. We could use this to make predictions. One of the things is, you know, what types of things do we like to predict for something like this? Well, one, we like to predict the rate at a given concentration of A, let's say. And so one of the things we do is, let's say if we consume half of our reactant, what happens to the rate? In this case, if we consume half our reactant, did the rate change? No. So the rate didn't change at all. We call that a zero order dependence on A. In other words, we come up with something like this. The rate is equal to K. K is called the rate constant, which is going to depend on the reaction itself, times A to the 0. And so in other words, the rate is equal to K, which is just equal to a constant here. We don't really need a special math to figure this out, because the rate is just equal to delta A over delta T, the negative of this, or the absolute value of this. And so what we end up with is this. We can rearrange this equation to come up with the mathematical equation. Well, actually, let me say what it is called. It's called the integrated rate law. And this one is called the rate law. Here. And so looking at the integrated rate law, there's really no special math involved here. K is equal to minus. Okay, delta A is A final minus A initial. Delta T is T final minus T initial. T initial is usually what? 0. Since T initial is usually 0, we call it just T, the time interval. And so this is just going to equal minus the concentration of A final minus A initial over T final minus T 0, which is just 0 here. And that means A initial is just A times 0. It doesn't have to be, but that's usually the way it is. And then if we continue to solve this, then we get A at time T, which is T final, is equal to minus K times T, that's K times T, plus A at time 0, where K is the negative of the slope. You see that? This is the negative of the slope. So this is called the integrated rate. And so we see that as the concentration changes, the slope just stays constant. And we see this. And so what can we predict with this? We can predict the rate at any concentration A here. We could predict the concentration at any time, or the time for any concentration. And so here, this allows us to predict concentration at time t, or time for a specific concentration. So if we want to predict the rate at any time, what we do is we first figure out, okay, the time, and then calculate the concentration. And from the concentration, we could figure out the rate. But the rate's simple here because the rate is not changing at all. So this is what we have here. Now, this is what we call a zero-order dependence on the concentration of A. So zero order in A concentration. And so this is called zero-order kinetics. Now, the next type of kinetics you want to familiarize yourself with is this. It's where we start off with A initial here, and then we cut it in half. It takes this long. And so this is called T1 half here. The time it takes to consume half of A. And then we start here and we cut it in half again. When we cut it in half, here, this is T1 half here. And we see this relationship. The relationship is that each time we cut this in half, it takes the same time interval. And so these are evenly spaced out, and this would be cut in half here. So. All right, so we get a curve like this. All right, now take a look at the previous, the straight line. What is the T1 half relationship there? Can you tell by looking at the curve how T1 half varies in the previous curve? On the linear curve. On this curve, each time we cut it in half, it takes the same amount of time. And so the T1 half intervals are all the same. Do you see that? We get a curve like this. What about on the previous curve, on the straight line? What is T1 half? What happens to T1 half each time you cut it in half?
It decreases.
It decreases, yeah. It gets shorter. Do you see that? It takes less time. And how much shorter? Can you tell by eyeballing it? What does the pattern look like? Half the time. And so you start off with a T1 half and a linear curve, the previous curve, like this. And the next one is half as long. And the next one is half as long. And so it just continues to get chopped in half each time. Do you see that? This one, the half-life, just stays constant throughout. And so these are different ways we could recognize the curve here. So we have this type of decay. This type of decay is called a first-order decay. The reason that this is called a first-order decay is because of how the rate, that is, the slope, varies with the concentration. And so here, we have our initial rate here, here, and then here, and here, which is pretty much the tangent. So when we predict the rate at concentration of A here, we're going to see that the rate is equal to K A to the first power. This is the type of dependence that's just observed mathematically. And so it's going to look like this here. In other words, what happens is if the concentration gets cut in half, that is, this concentration gets cut in half, then the rate would get cut in half. And so an example of this dependence, let's show over here. If the concentration at time t equals 1/2 the concentration at time 0, then the rate is equal to K, the rate constant, this is called the rate law, times A, the first. Okay, this is A at time t, but A at time t is just 1/2 A at time 0. And so the rate is 1/2 the original rate, K A at time 0. If we cut the concentration to 1/4, then the rate's going to be 1/4, the 1/2. And so in other words, this would be called a first order dependent here. And that's how to make things. Okay, so we can predict the slope or the rate at different concentrations, you know, if we know what K is. Now, the next thing we want to be able to do is to predict the concentration at any time t, or the time it takes to reach any concentration. And so the question comes out, you know, what is the mathematical definition of this line? No. Is there an equation that fits that line? Like, well, obviously y equals mx plus b won't, because that's linear, but there must be some other mathematical definition. So what we could do is we could do curve fitting, or we could do calculus. Right? And so there are different ways to handle this. One, curve fitting. Are you guys familiar with curve fitting? We just try to fit it to a mathematical equation, and then we see how good that fit is by calculating a statistical factor, so like the R squared value. Have you heard of the R squared value? R squared value just tells us how good of a match our experimental data or experimental line is to that mathematical equation. And so we could try curve fitting, or you could use some calculus to derive it. And so if this is the rate law, you know, the problem is the rate is always changing. So we have delta A over delta T negative. And so this is always changing. And so it just simply isn't a matter of just solving this, you know, for A final. And so this is why we need calculus. Since this is always changing, what we do is we get the integrated rate law. Using calculus to come up with the equation for that line. And so the equation for this line, there are different ways that we write it, but the typical way that we write this is ln of A at time t over A at time 0 is equal to minus kt. And so what this allows us to do is it just allows us to calculate the concentration at any time t, or calculate the time interval required to hit that concentration at time t. This is called exponential. Okay. No, it's first order. Okay, now the next one we're going to have is going to look like this, where let's say one half-life takes this long, T1/2, and the next half-life takes twice as long. And so this would be 2 times the original T1/2. And then the next one, we have to double the previous one. So each successive half-life is doubled. And so we get a curve like this. When we look at what happens with the slope, if we cut the concentration in half here, like this, then the slope gets cut by a quarter. The slope is the rate. So let's take a look at the rate law here. the rate is equal to K, or rate constant, times A. And this is the second order. With respect to the concentration of A here. And so in other words, we could go backwards here. Let's start at this concentration. If we start at this concentration and double the concentration, if we double the concentration, then the rate quadruples. Or if we go forward here, we start here and cut the concentration in half. If we cut the concentration in half, then 1/2 squared is going to be 1/4, so we'll have 1/4 of the original rate. Does that make sense, or do I write that out? Okay, now what we want to do is we want to figure out what is the equation that defines this line. And so the equation that defines this line is we could use curve fitting or some calculus here. We're going to use the calculus, and that is we're going to get the integrated rate law, which we're skipping the derivation of this, but you can look in your book for that. And so when we derive the integrated rate law, it looks like this. 1 over A at time t is equal to plus kt plus 1 over A at time 0. And so this shows a second order of dependence on A. So now we can make predictions. With the rate law, we can predict again the rate at any concentration. With the integrated rate law, we can predict the concentration at any time or the time required to reach a certain concentration. And so these are the equations we need to solve the kinetics of this. So let's look at an example here. An example would be something like this. A goes to product. There could be multiple products here, but we're just looking at the decomposition reaction of A. Like hydrogen peroxide. Hydrogen peroxide decomposes into water and O2 gas. And so this would be similar to that. So if we're looking at the decomposition of A, then we can look at different patterns. And so one scenario might be it decomposes like this. If it decomposes like this, is that a zero, first, or second order decomposition? It's a zero order decomposition, so we can just eyeball the graph, right, and see. Sometimes it's difficult to see. When it's difficult to see is, let's say I had, instead of data points all spread out like this, let's say I just had an initial cluster of data points like this. Now, is this zero, first, or second order? It's hard to see, right? Because, any little error will result in a big error in predicting this. Whereas a little error here, if I spread it out and I have a little error here, a little bit of error here, that's not going to make that big of a difference because you can pretty much see that it's pretty linear. Right? And so here, when I have a tight cluster of data here, it compounds the error. It makes it much more significant. But if I spread it out over time, it makes it much less significant. And so if I have something like this, how do I know? Is that zero, first, or second order? Those are the only three choices we're going to consider right now for this type of reaction. And so let's say I have something like this, and I don't know how it's going to. Is it going to curve like this, or is it going to just keep going straight? And so these are the ways we're going to deal with determining the order with respect to A. the easiest way of determining the order is to do something called the method of initial rates. The initial rate, let's define that first. The initial rate is defined as the rate at time 0, which is equal to the tangent at t equals 0. And so in order to determine the initial rate using this, what we have to do is we have to draw the tangent line here, right? And then figure out what is the slope of the tangent. Take the negative of that, that would be the initial rate. But doing that is difficult sometimes because drawing a tangent at time 0, you don't have the rest of the curve to really be able to estimate it accurately sometimes. And so what we do instead is we just say it's approximately equal to the average rate as long as less than 5% reaction has occurred. And so what does that mean? That means this. That means that if I'm starting at 1.000, then I have two choices for determining the initial rate. What are my two choices? One, draw the tangent here. Or two, make sure that by the time I hit 0.950, I'll take the average slope, of one of these here to get it. Does that make sense?
What is the average slope? You do 2 points?
Yeah, you just pick 2 points. So the average slope would be this. We have the concentration of A versus time. And so if we start off at 1.00 and time 0, let's say at 5 seconds, it goes to 0.98, right? At 10 seconds, it goes to 0.94. And so if you do this, if we just take the slope between the first and the third point, how much reaction has taken place? Between the first and the third, how much reaction has taken place? Well, you should be able to eyeball this. If we start off at 100%, we're down to 94%. And so 6% has reacted. Does that make sense? So if I took the average slope here, that is, I just calculate my delta y over delta x. That's the average slope for the first 6 seconds of reaction. I mean 6% of reaction, not 6 seconds, sorry. First 10 seconds, which is 6% of reaction. It's too much. That's getting too far away. And so what that looks like is something like this, where here, the first point and this point, we get the average slope that looks like this here. That would be the average slope there. But really, we should have gone at 5 seconds here because it was 0.98. Something like this. I think I screwed up the numbers, but it's okay. Versus something like this. You see, at 6% of the reaction, it's starting to level out more, but at less than, this is only 2% reaction that's taken place. Right? Do you see it's a little steeper drop here? Does that make sense? Versus the tangent. The tangent would be the true initial rate, right? The initial rate is supposed to be right here. And so if this rate is changing, let's say the rate is getting slower, right? at time 0, you're going to have the fastest rate because you have the highest concentration. But as the concentration decreases, the rate slows down continuously like this. And so we don't want to wait too long, because if you take the average, we're going to get further and further away from what it was initially. Does that make sense? And so what we could do is we could average these, because this is 2% reaction. However, if we average these, we got 6% reaction, which is too much.
Can you use any interval window, like say from 0.98 to 0.96? Can you average those scores?
You can't easily. You can't do that easily, because in the method of initial rates, this is what we do. We do the method of initial rates because we have control over only one concentration. What concentration do we have control over? The initial concentration. But any other concentration, you're just waiting for it to hit that, right? Like say, for example, I don't want to start at 1.00. I want to start at 0.95. But you know what? My data just missed 0.95. Where's 0.95 going to hit, right? And so if I'm starting at any other interval, what I'm doing is I'm starting at a different concentration. How can I reproduce that concentration? And how do I know if I'm going to get a data point at that particular concentration? Because it's okay for one, because maybe I'll say, no, not 0.9, I'll go 0.98 right here. I have a data point at 0.98. And so why don't I just do this interval, 0.98 to 0.94, right? And figure that out. Now the trick with the method of initial rates is this. What we want to do is we want to double the concentration. If we double the concentration, then we're looking for three things. If we double the concentration and the rate stays the same, we call it zero order. If we double the concentration and the rate doubles, we call it first order. If we double the concentration and the rate quadruples, then it's second order. Those are the three possible scenarios we're looking for. Now, if we start at 0.98, how am I going to double it? Because if I double that, then I need 1.96. Well, how am I going to get 1.96? I guess I could, start it at 1.96. The next one, but it turns out not to be so easy. So the best thing is to collect data and make sure you get the initial rate here. Okay, so we get enough data to get the initial rate. We aren't going to watch how this whole thing decomposes. The other alternative to this is just wait until it gets to 0.5, and then wait until it gets to 0.25. And so we go from 1 to 0.5, it takes this long. And then 0.5 to 0.25, look how long it takes. You only have three choices. The second T1/2 could be the same. If it's the same, we call it first order. I'm going out of order. If it's the same, it's first order. If it gets cut in half, that's zero order. If it doubles, it's second order. And so the problem with waiting is you might have to wait a very long time for slow reactions, right? And so the advantage to this method is you only have to collect the initial start of the reaction, and that's it. The disadvantage to this is you have to do multiple experiments. Actually, it's hard to say which one's more advantageous, because we haven't talked about another technique. Another technique is I could just go ahead and use these first 3 points here and figure it out a different way by curve fitting. I'll show you what I mean by that. All right, so what we do is we get the initial rate at what we call concentration 1. And then double it. concentration 2 equals 2 times the concentration of 1, and determine the new initial rate. If we double the concentration and the rate is unchanged, then it's a 0 order. Rate is double, then it's first order. Rate is quadruple, then it's second order. Okay, then once we have the rates, then solve for K. Actually, I already said then. Next, solve for K. And so K1 we'll get is equal to the rate 1 divided by the concentration of A to whatever power this is. We'll call it the M power. K2 equals the rate 2 over A. This is A1, this would be A2 with N power. And then we average those. We get K average. And so what we end up with is the rate law. The rate is equal to K average. The K shouldn't vary. The K should be constant for this particular reaction. A to the either the 0, first, or second power. Okay, we'll do an example of that later. Okay. The next thing we could do is we could collect a lot of data. And so that was method 1. This is method 2. We collect a lot of data. And so we have A versus time like this. And let's say we have lots of data here. All right, then what we're going to do is we're going to use Excel and calculate the ln of A. Okay. Calculate that. And then we calculate 1 over A. Yeah. Calculate that. And so we'll just take the natural log of A. And then we determine which of these three, if we plot it against time, is most linear. And so we generate 3 plots. We generate the A versus time plot, the ln of A versus time plot, and the 1 over A versus time plot. Determine which is linear. Just say most linear, or maybe I should say linear. Determine which is linear, and then we have the order. And so if the A versus time plot is linear, then we know it obeys this law. Concentration of A times T is equal to minus KT plus concentration of A times 0. The ln of A versus t plot comes from this. If we have ln of a at time t, we'll just take the integrated rate law. It's ln of a times t divided by a at time 0 is equal to minus kt, which means that the ln of a at time t is equal to minus kt plus the ln of a at time 0 using the property of logs. And so when we look at this equation, this is the y equals mx plus b form, so this makes it linear here. And so if this one comes out linear, then it's first order. If this one comes out linear, this one's going to have the opposite slope. This would be a positive slope. Then it's second order because this one's defined as 1 over a at time t is equal to plus kt plus 1 over a times 0. And so what we do is here, we do a linear least squares fit. It's the easiest thing to do. Linear least squares fit of each. Linear least squares fit of each to determine which has an r squared. R squared is the correlation factor. It's how well these data points correlate with the straight line. It has an r squared, a perfect correlation, which has an r squared closest to 1. 1 is a perfect fit. But be careful, because r squareds less than 2 nines aren't very significant. Like an r squared, but be careful, because an r squared you might think of 0.90 as being pretty decent, like 90%. But an r squared of 0.90 is a bad fit. Typically when we're looking for r squared values, we're looking at multiple nines, 0.99, etc. This is what we want. And so if you're getting an r squared value of 0.8, it's pretty much no correlation. 0.8, 0.85, that kind of stuff. Something must be wrong. The problem is are you going to have a computer on the test? Can you have graphing calculators on the test? No. And so we have to come up with an alternate method for this. And so this is method 2. And so method 3 is one you're typically going to use on an exam. How much data do we really need to determine if this is a straight line or not? 3 points, right? And so let's see. But the more points we have, the less prone we are to error. And so here, minimum of 3 points. Now, if you have a computer, then figuring out linear fit is pretty easy, right? Because you just say, fit this data to a straight line and give me the r squared factor. But what we're going to do is we're going to do a manual fit to this. And how are we going to do a manual fit? The way we're going to do a manual fit is we're going to calculate the slope. Let's say I only have 3 data points. If I have 3 data points, then I calculate this slope here, right here. And then I compare it to the next slope here. If the 2 slopes match, then you'd say it's pretty linear, wouldn't you? Right? Okay, then over here, I would compare the first segment slope to the second segment slope. And the same thing here, first segment slope to the second segment slope. And so whichever slopes have the best agreement, I'm going to call, that's my most linear fit. This is always subject to error, because if you have some, let's say you have some experimental error that kicked up this data point, then maybe it's going to look like the slopes don't match, but that was because of fluctuations in the data. So you have to be very careful with this. Because if you're getting a lot of fluctuations, then it depends on when you recorded that measurement. You know, when you recorded the measurement and it was like this, then well, it doesn't look so good. Or when you record the measurement and it was like this, and it looks pretty linear. And so hopefully you don't have big error bars, which would screw up this analysis. The other thing is, if you can widen out. If you can widen it out, you know, let's say the first interval was like this, a very large interval, and then the second interval was very large, then the error will be minimal. You know, the most error we're going to see is right at the beginning. You know, if I have 3 data points that are clustered very tight, then like we were talking, a 1 drop error is significant, right, here. But if I had 3 data points that are separated by wide distances, then it's easy to see, whoa, this is going to curve up. You know? And so we got to worry about that. But anyway, we have a minimum of 3 points, and this is how we do it. This is called slope analysis. For slope analysis, I'll just do the concentration of A. All right, calculate. This is the original data, right? Original data. And then what we do is we calculate the ln of A. Calculate that. And then we'll calculate 1 over A, just like we did before. Calculate this and this versus time. And so here, you know, I got a point, we'll call it point 1, point 2, point 3, then ln of 1, 2, 3, and then 1 over A, 1 over A, 2, 1 over A, 3. And this is T1, T2, T3. Like that. So all we do here is we do this. We calculate delta concentration here over delta T. And so I'm going to call this A, and delta TA. And so this will be the first segment. And so we're going to look at slope for segment A. And then we look for the slope for segment B, delta B over delta TB. And then we just compare these 2 slopes. And so here we're calculating for slope A, we're calculating the concentration of 2 minus the concentration of 1 divided by T2 minus T1. For slope B, we're calculating the concentration at 3 minus the concentration at 2 over T3 minus T2. And then what we do is we calculate the percent difference between these two. Percent difference is equal to the bigger value minus the smaller value divided by the smaller value times 100%. Okay, this is for zero order. If it was a zero order dependence, then this concentration of A versus time should be linear. All right, after we do zero order, then what we'll do is we do first order. So for first order, it's probably easiest not to use this. For first order, normally the way I do this would be this. It would be K. And so rather than calling this the slope, you know, it could be slope analysis or K analysis. The only difference between the slope and K for zero order is that K is the negative of the slope. And so that would make it K analysis. Right? For first order, K is equal to what? Is the negative of the slope again. And so K is negative of the slope, but K is also equal to ln of A at time t over A at time 0 divided by, now I'm going to get t, and I've got to put a negative sign here. And so essentially all I'm going to do is I'm going to calculate this. Rather than call it the slope, which it is the slope, I'm going to call it K for segment A and K for segment B, which is the slope, the negative of the slope. All right, so K for segment A is going to equal this. It's just K for segment A is minus Ln of, okay, the final concentration will be 2, the initial concentration is 1, divided by the time interval, which is T2 minus T1. And then K for segment B is equal to this. KB is equal to minus Ln of concentration at 3 divided by concentration at 2, T3 minus T2. And so essentially what I'm doing is this. K is supposed to be a constant. And so what we're going to find is it's only a constant for one of these scenarios. And so if the K changes here, i.e. the slope changes, then it's likely not zero order. Whereas if the K stays constant here, or i.e. the slope stays constant, then it's first order. Right? And then if it's first order, then this would be changing, and the slope, or K, would not be constant. And so again, what we're going to do is we're going to calculate the percent difference. Percent difference. Okay. And then compare. You know, which ideally the percent difference should be 0 if it's linear. You know, that shouldn't be changing. That's first order. And then we go on to the next one, which is going to be second order. For second order, the slope, or K, is equal to 1 over A at time t minus 1 over A times 0 divided by t. And so K for segment A, that is the slope for segment A, is going to look like this. It's going to be 1 over A at time 2 minus 1 over A at time 1 divided by T2 minus T1. And then for segment B, the slope, or K, is going to equal 1 over the concentration at time 3 minus 1 over the concentration at time 2, T3 minus T2. And so all this writing, and all we're doing is we're comparing the two slopes, you know, between the first 2 points and the second and third point. Does that make sense? That's all we're doing, is just comparing the slopes. But the way we're going to do this is sometimes it's hard to tell, like I said, because at the beginning of the reaction, everything's clumped up. And so we're going to calculate the percent difference here. Then we're going to determine the smallest percent difference. Should give us the order of the reaction. You know, in other words, the smallest difference in the two slope segments, that should be the most linear. You know. So what was the first method? The first method for determining the order was the method of initial rates, right? The second method was to graph it. The third method is this slope analysis or K analysis. The fourth method works on, sometimes it works on multiple choice. Method 4 is if you have a lot of data. You know, you don't just have 3 points, but you have some initial, and then you have something that's roughly 1/2 the initial. And then you have something that's roughly 1/4 the initial. And so this is the eyeball data method. The eyeball data method is for multiple choice questions. You know, if they're asking you what the order is and they give you a data table like this, then you probably can eyeball it and see. Because if you take an initial and there's something roughly half of that, and then there's something roughly 1/4 of the initial, then you can see how long did it take here. Maybe it took 6 seconds. And then let's say to get to 1/4, it was 12 seconds total. So if it was 6 seconds for this and another 6 seconds for this, then we know what it is. It's got to be first order. If it's 6 seconds for this and it's 3 seconds for this, then it's got to be zero order. And if it's 6 seconds for this and 12 seconds for this, then it's second order. And so those are the 3 possible scenarios. And so we look at T1/2, and then we look at the next segment. You know, we have 3 choices for the next segment. One, it could be 1/2 T1/2, which is zero order. Or it could be equal to T1/2, which is first order. Or it could be 2 times T1/2, which is second order. Unfortunately, we don't have this much data all the time, but if we do, then it's easy to see what the order is. So let's see an example of actually. For example, yeah, let's do an example of this now. Someone have their book? If they tell us what order it is, then it's pretty easy. You know, but sometimes they don't. You have the hydrogen peroxide in the chapter itself. There's a data table for hydrogen peroxide. In chapter 14.
peroxide.
Yeah. Is there a data table for that? You know? Oh, that. Near the beginning. Yeah, okay. Let's go with the first set of numbers there. All right, they give us the time, right, versus the hydrogen peroxide concentration, is that correct?
Yeah.
Okay, what's the first time, 0?
0.
And the hydrogen peroxide?
2.32
Okay, the time is in seconds or minutes?
seconds.
And the hydrogen peroxide is in molarity.
Yeah.
All right, the next time,
200.
200 and
2.01.
2.01. And the next time,
400.
400 and
1.72.
1.72. All right, let's stop. I'm only going to use the first 3 data points right here. You know, the best thing is to use all the data, because if we use all the data and graph it, then when we're doing a linear least squares fit, we're averaging every single data point, which is going to help minimize random error. Random error sometimes is a little high, sometimes it's a little low. So the more data we have, the more that averages out. And so the best thing is to go ahead and plot out all the data. But unfortunately, you aren't going to be able to do that on a test. On a test, which method can you use? Can you use the eyeball data method? Can you just eyeball this data and tell me what the order is? No, fortunately not. You're going to have to use the, method of initial rates. Can we use the method of initial rates? Well, how much decomposed in this first interval here? 0.31 out of 2.32 decomposed. So what percent reaction happened? More than 10%?
Yeah.
That's more than 10%. We can't use the method of initial rates here, can we? And not only we can't use the method of initial rates here because more than 5% reactions occurred, so we can't really get the average slope there right at the beginning. And we have one more problem. The other problem is in the method of initial rates, you have to double the concentration or cut it in half or do something, right? To see what happens, but we only have one experiment here. And so we can't do that. And so that leaves us with K analysis. K analysis. So does K analysis sound pretty straightforward? Or do you want to go through it? Yeah, basically this one you're going to have to do K analysis. Let me just leave it here like this. Versus, sometimes what they do is they make life a little bit easier for you. If you wanted to do the method of initial rates, we would have needed 2 experiments. And so let me talk about that just briefly here. In order to do the method of initial rate, that requires work, right? Because what we have to do is we have to do experiment 1. Experiment 1, let's say we're starting off at 232. And so this is 0, 232. This is time, this is concentration. And then let's say we need to make sure we collect data a little quicker, don't we? Because we had too much decomposed. And so we probably take a data point rather than waiting until 200 seconds. We should have taken it maybe at 100 seconds or less, maybe at 50 seconds. Tighter intervals we would have needed here to collect more data. And so we do experiment 1, and then how do we calculate the initial rate? There are 2 methods to determine the initial rate. What were the 2 methods to determine the initial rate from our data here? Yeah, what we do is, etc. We would plot this. Hopefully less than 5% reactions taking place, so we can just take the slope between these 2 points. The average slope between these 2 points, as long as it's near the beginning, would be considered the initial rate. Otherwise, we'd have to take the slope of the tangent line, right? And is drawing the tangent line something so easy to do? No. All right, that's experiment 1. And so what we'll do is we'll repeat the experiment. We'll go to experiment 2. And this time, what we're going to do is we're either going to double the concentration or cut it in half. It doesn't really matter. If we double it, we'll go to 464, 0, and then maybe collect data rapidly here. And then hopefully we get a lot of data right at the beginning here so that we can calculate the initial rate here. And then what we do is we compile it into a table that looks like this. This is the method of initial rates table. In the method of initial rates table, it's going to look something like this, where we'll have the experiment over here. Experiment 1 started off at a concentration of 232 and gave an initial rate. Why the initial rate? Why not just any old rate? Why does it have to be the initial rate? That's what we can control, right? We can only control the concentration right at the beginning because immediately once the reaction starts, the concentration rapidly changes, it decreases. And so the initial rate, we call rate 1 here. And then here, experiment 2 at 464, and then we look at rate 2. And then we just look, did it stay the same? Did it double? Or did it quadruple? We check it. Does that make sense? That's what we do, but we can't use the method of initial rates here. We're going to use the K analysis here. And so this is just the side. All right, the next thing, what time do we go till? 55. Are we okay with this so far? 0, first, and second order. The equations for 0, first, and second order, we don't have to worry too much about yet.
I have a question.
Mhm.
So for this example, what would the question be asking for?
Okay, what would the question be asking for? The question might be asking for, at 1,000 seconds, what is the concentration? And so in order to figure out what the concentration is at 1,000 seconds, how are we going to get it? And so let's go ahead and answer. You want to answer this? All right, how are we going to get it? Or, at 1,000 seconds, what is the rate of the reaction? Or, how long would it take to consume 90% of my hydrogen peroxide? How long would it take to consume 90% means I want to go from 232 to, just 10% of that, which would be 0.232. I would be consuming 90%. And so these are the types of questions we want to answer, but the problem is this. These questions are very easy to answer if it's linear. If it's linear, it's just a y equals mx plus b. The rate doesn't change. The rate between this segment and the rate between this segment is the same as the rate between any segment. So the rate just stays the same. And then to figure this out, if it's linear, then we just use a zero order. Concentration of A at time t is equal to minus kT plus concentration of A times 0. But we don't know if it's linear. we have three choices of curves: linear, exponential, or this second order. You know, in other words, zero order, first order, and second order decay. And so the first thing we have to figure out is, what is the order? And we have four methods that we could use to determine the order. And the method that we have to use is K-analysis. We could do K-analysis. Should we? All right, let's do K-analysis here. Let me make some room. Or I'll just leave this chart here. And so the first thing is, you assume it's zero order. Okay, if it's zero order, then we're going to call this, you know, K for A, and then we'll call this K for segment B, and then C, because they match. We can also have a K for segment C, like this, that is between the first and third, too, but it should be between these two. There should be a more extreme difference between these two. And so these are two convenient ones we can look at. And so for zero order, the equation of the line is like this. A times t is equal to minus kt plus a times 0. We're going to just call this K analysis now. K is equal to a times t minus a times 0 over t, and then multiply this by negative. And so let's look at K for segment A. And so this is what we do for the calculation. Here, I'll do the calculation with you. The calculation is 201 minus 232, but since we're taking a negative, I can do this one in my head, fortunately. 0.31. So it's going to be 0.31. And the time interval, 200. So divided by 200. And so K for 1 comes out to 0.00155 molar per second. Okay. K for B is the difference between these two, 29. Is that right? 0.29, and the segment here divided by 200. It comes out to 0.00145 molar per second. Hey, does that look pretty the same? Close enough? Well, it's hard to say. Let's try a different one. You know, I don't know, 155 versus 145. Maybe they're close enough. Maybe not. Let's see if there's a better. And so, the first thing we'll do is we'll calculate the percent difference. The percent difference is the biggest, 155, minus the smallest, 145, which is just 10, divided by the smallest, 145, times 100%. Get that right. 10 divided by 145. Percent difference. 6.989. Sorry, 6.89%. Pretty close? It doesn't seem so close. All right. Let's try first order. Maybe it's a little better. And so trying first order, you know, we got the equation ln of a times t over a times 0 is equal to minus kt. Solve this equation for k. K is equal to ln of a at time t over a at time 0, which is initial, divided by t, take the whole negative of this. And so what I do is I do this in the parentheses first. And so looking at Ka, I'll do 201 divided by 232 equals, and then take the natural log of that, ln, and then divide it by 200, and then change the sign. So Ka is 0.000717. Out loud. Oh, that's probably okay. Okay, let's look at KB. I might have to take more digits out. And so KB is 172. 1.72 divided by 201 equals, take the natural log of that, divided by the time segment, which is 200 again. It's not always 200. This comes out to 0.000779. Which one do you think is a better agreement? Zero order or first order? It looks like zero order is better because there's only a difference of 10, right? But you have to be very careful. This is a difference of more like 60. And so a difference of 10 looks better than a difference of 60. But it's not, because this is a difference of 10 over 145. And so 10 parts out of 145 versus 60 parts out of 700. So which one is better? 60 parts out of 700 or 10 parts out of 145? Well, let's see. So rather than having to think about it, let's just calculate the percent difference. If we calculate the percent difference, it's going to be the biggest, 779, minus the smallest, 717, divided by the smallest, 717 times 100. 8.64%. 8.64%. Is that right? So far it's looking like zero order. Okay, next let's go to second order, because maybe second order is better. Because I'll tell you, this is not so great either. You know, let's say, I calculated my percent difference. My percent difference for this was 5.8. And my percent difference for this was 5.9. Oh, 5.8 is better than 5.9. It's got to be 5.8%, right? What would you say to that? They're both bad. They're both not great, right? And so you have to be careful of that. So maybe second order is better. So let's try it. Second order. Oops, I don't want to make a table. Second order is going to be 1 over A times T is equal to plus KT plus 1 over A times 0. Solve this equation for K. K is equal to 1 over A times T minus 1 over A times 0 divided by T. And so we use the invert key on the calculator for this. And so I'll just enter it in. A times T is 2.01. So I do 2.01 invert minus 2.32 invert equals, divided by 200 is the time interval, and I get Ka of 0.000332, and then Kb, we'll do it again, 1.72 invert minus 2.01 invert equals, divided by 200, and it gives me 0.00494. I'll just do 419. And so if we calculate the percent difference here, it's 419 minus 332. So I'll do 419 minus 332 divided by 332. 26.2%. That's off, right? It's considerably off. And so what would you say? You'd say it looks to be zero order. But are you so happy with that? When you're getting the differences between 7% and 9%, right? And so when we're looking at that, it's hard to say which one is right, because both of them are not very linear. And remember what I said about the beginning. At the beginning, you could have error. And so the best thing to do in a scenario like this is to collect more data and spread it apart. And so what we're going to do next is we're not going to pick the first 3 points because they collected more data. We're going to spread out the points, let's say, and then see. Because when you plot out all the data and you see this curve, what does the curve look like in your book? Maybe you don't have your book with you. But right now, based on our data, it looks to be first order. I mean, zero order. Zero order. Zero order. But there are other things that, from experience, if you have like a fresh bottle of hydrogen peroxide and you left the cap off, and this is just based on experience. I don't know if you have experience with hydrogen peroxide, but do you think it decomposes linearly? Or do you think it kind of starts to slow down? It starts to slow down, right? And take more time. Mhm. Are you?
I think I heard you say 1.72 instead of 1.7. Because I'm not getting the 0.00419. And the percent was actually 3.4. 7.6.
Oh, all right. Then I might have made a mistake. Let me double check those. Well, actually, let's see how much reaction is taking place here. More than 10%. What did you get here? You're saying for this one?
No. Oh, it's all right.
This one here?
Yeah.
Actually, double check my calculations here for all of them and see if it's correct or not. And then we'll discuss this more next time.